Okay, welcome back everyone. Before I continue with the plan, I want to make a few comments about what I said yesterday. Someone asked about whether the timings were in seconds or milliseconds. In fact, they are in milliseconds. I checked that last night, which explains what the threshold is 5 minutes. Someone else asked about why we don't use simply projection once we have computed the V representation, because then it's obviously trivial. But because here the goal is really to obtain H representation of the output, that is obtaining a system of linear inequalities. So that's why we focus on that. That's really what is important in applications. Okay, so this was about yesterday's questions. So today I will talk mainly about the lattice points, or the points with integer coordinates of polyhedral sets, discussing essentially 3 aspects. So first, computing the integer whole of a polyhedral set. That's the first way of describing its integer points. Then I will move to the problem of counting integer points without computing them, because there are many applications where this is sufficient. And after that, we'll move to quantifier elimination over the integers, that is Presburger arithmetic. And as I'm doing that, I will in fact describe another way of describing the integer points of polyhedral sets. Also, I've made a few updates on the slides, but I could not connect to my server this morning, so hopefully later today I will manage, and then you will get a much more debugged version of the slides. I will also show Maple worksheets, but most of them are in fact part of Maple. Okay, so let us start with integer wholes. So I mentioned the problem of dependence analysis yesterday. Here is a less trivial example than the one I was showing yesterday. So this is one version of LU decomposition, so more precisely the Cholesky LU decomposition. And so one natural question is whether we can parallelize the second for loop between line 3 and 4. In order to do that, we have again to check for dependencies. If we look at the expressions that are in Bordeaux and in blue, we may ask whether we have some dependence of type read after write or write after read. So is it possible that at 2 different iterations of the for loop, we are reading something at 1 iteration and writing that same memory location at another iteration? Okay, so this is the question. This is solved by setting up systems of linear inequalities and equations, which I'm showing here. So we have to distinguish 3 cases, but I'm not going to enter the details of that. And so for each system, we are asking whether we have integer solutions. And for that, it is enough to compute the integer whole of the corresponding polyhedral sets. So remember that I have some challenges with Beamer. So that's why I have the word null, null, it's written everywhere. I think I have too many slides, I'm using too many packages. I will also try to fix that, of course. Okay, so this is what we want to do. So let's give a few definitions around the integer whole. So the integer whole of a polyhedron P is the smallest convex polyhedron containing the integer points of P. So here we have a simple example. So our input is in blue. This is a polyhedron, and we want to describe the red polyhedron, which corresponds exactly to the integer points of the blue polyhedron, and in particular, its vertices are integer points. So another way to phrase that is that Pi, the integer whole, is the intersection of all convex polyhedra containing the integer points of P. And when P is pointed, then P equal Pi, so P is its own integer whole if and only if every vertex of P is an integer point. Another example, here we start with, again, a blue polyhedron. So you can see where the corresponding facets are on this illustration. And then in red, we have the points that we want to compute, which are again described by another polyhedron, the facets of which are in red. In fact, in the algorithm we are going to describe, we will not compute the facets, we are going to compute the vertices of the integer whole. The notion of integer whole is, of course, deeply related to that of an integer lattice. So for us, an integer lattice would be a set of integer points given by an expression like on the second line, that is, it's something of the form a matrix A times a vector T of indeterminates plus a vector B. So anything that looks like this will be for us an integer lattice. And integer lattices, they are natural ways of solving system of congruencies. So here we have X and B, which are two vectors, and A is a matrix. And the tool behind all that, as we can guess, is Hermite normal form. So I will review that quickly. I believe that we are all familiar here with that. So starting with a matrix C with integer coefficients and a vector Q. So my matrix has R rows and D columns. I'm assuming that C is full rank and R is less or equal than D, but these things can be generalized, but I will not need to explain that here. And so what we are trying to do is to find the integer solutions of the system C times X equal Q. And this is done by computing a unimodular matrix U, so that C times U, as we can see, is a bunch of 0 columns followed by the column style Hermite normal form of C. For what follows, it's convenient to write that unimodular matrix into two parts, UL and UR. The format of UR is it has D rows and R columns. Once we have that, we have the following properties. So first, as we all know, so H is non-singular. Moreover, the set of the integer points solving Cx equal Q is non-empty if and only if the inverse of H times Q is an integer vector. And moreover, the set of these points can be described by this formula here, where we make use of these two parts of the unimodular matrix, UR and UL. So we have a description, which is in fact a lattice in the sense that we reviewed just before. Okay. And these results can be generalized to the case of matrices of arbitrary ranks and format. See the work of Ernest Orjohan and others. Okay, so now the last object that I need to introduce is Z polyhedral set. So this is simply the intersection of a lattice and a polyhedral set. In other words, this is a subset of the integer points of a polyhedral set. Sometimes this set is empty. So of course we want ways to detect when this is happening. And for that it's convenient to have a notion of normalized Z polyhedral set. So something for which we would know that the thing is not empty, and in fact so that we have actually additional properties that to some sense feels a little bit like a lexicographical Grosvenor basis or a regular chain. That is something that describes in some ways the solutions or the points of that Z polyhedron. So we call such Z polyhedral set normalized. So they have the following shape. If the variables are denoted x1 through xd, and we can present a description of the solutions as we can see, where the AI are max expressions of linear polynomials, that is polynomials of degree 1 or constant, and the BJs are mean expressions of also linear polynomials. Or maybe just a constant, or maybe just plus infinity. And moreover, so we can, if we want, enumerate all the solutions by doing back substitution. So this is why it feels like a Lex-Grosvenor basis or a regular chain. So what do I mean by this? So let's say that variables are ordered x1 through xd. Then we expect, of course, that the bounds a0 and b0 are either plus or minus infinity or numbers, rational numbers. But then we know, obviously, what are the possible integer points there. For each value of these integer numbers, we can substitute that into the formulas of a1 and b1. And then again, that gives us a range of rational numbers where we know where the integer numbers are, and so on and so forth. So in this way, we feel that we have a good description of the integer points of such Z polyhedron. And we will see, as we do the quantifier elimination algorithm, how this is done, because in fact this is the same algorithm doing both. And this is implemented as the integer point decomposition in the Z polyhedral set package of Maple. Okay, so I will talk a little bit about the integer whole algorithm. I mentioned it yesterday. Okay, let us start with, I would say, middle school type of math. So we have a triangle. The vertices of which are not integer points. And so the question is to find the integer whole. So a first step in the algorithm is to ensure that the supporting hyperplanes of the facets have integer points, which is easy to check. So for instance, for this facet, its supporting hyperplane does not have integer points. Then we slide it towards the center until it reaches a parallel line that contains integer points. So we do that with each facet. Of course, this transformation does not change the integer whole. And once we have that, so we are ready to start. Yes? So we move the facet until the supporting hyperplane contains integer points. That does not necessarily imply that the facet will contain integer points. When this happens, so there are workarounds on which maybe I will slide a little bit here, but I will try to give you some ideas. But thank you for the question, because that's an important point. But the algorithm, yes, works with all situations. So here, for simplicity, I will assume that each facet after this transformation contains integer points. Okay, actually I will be able to answer your question more precisely here. So here we have a simple example where each facet after this normalization phase contains integer points. If, let's say, the southeast facet would not contain integer points, then the decomposition that I'm going to explain, instead of using these points that it does not have, we'll use points that are on the other side of the triangle. So let me explain what is this decomposition. So in this ideal scenario where every facet contains integer points, so I'm going to mark them, I can easily find them, and these are trivial calculations. And then I am left with these little corner regions which maybe contain integer points, maybe. Okay. What I know for sure is that the polyhedron with red facets is its own integer whole because all its vertices are integer points. So I'm happy with that. I can see it as a sort of approximation of the integer whole. I still need to inspect these little corner regions. Okay? For those, I'm going simply to use brute force. So that is, I will, for each of them, apply Fourier-Motzkin elimination. So that is, from the vertices, I deduce the edge representation. Then I get a system of linear inequalities by Fourier-Motzkin elimination. And then I can easily try all possible integer points. This is gross, but these regions are small. So in practice, that works well.
You know exactly how small?
So for large objects, let's say the distance between 2 points is in the 1,000. Yes, they will be, on average, relatively small. I mean, experimentally. Okay. If the whole thing is small, okay. But by the way, the other algorithm for integer whole essentially do similar things. That is, they do some preparation work, and after that, they run Fourier-Motzkin to find the points. So here we are trying to avoid it as much as possible. Or if we do it on this small region.
And then you run with
Exactly. Okay. Exactly. So in fact, the difficult part in this algorithm is obtaining that partition. So actually, I'm not going to explain how it's done in general. I would refer to the PhD thesis of my student, because I have not managed for the moment to write it in some clear ways for slides. Okay, in the thesis, I hope it's well written. But so to summarize, the algorithm has 3 steps. There is this normalization step where we slide the facets toward the center until we are certain that their supporting hyperplanes contain integer points. Second step, we compute a partition. This partition consists of a big part, so the red part on the previous picture, which is its own integer whole, and then some small regions that we have to explore by brute force. And after that, yes, we run an algorithm like a quick roll to determine, finally, the vertices of the integer whole of the input polyhedron. Okay, so I'm showing again the example of yesterday. So I start with a gentle pyramid here with 4 facets. Here we show one normalization step, so sliding one facet towards the center until its supporting hyperplane hits integer points. Oops, yes, so I will skip the description of how we compute the partition. So it's on the slide, but it's a bit technical. And after that, yes, there are these regions which are typically thin. Which again are explored by brute force. And after that, we run quick hole, and this example is interesting because at the end, the integer hole has 139 vertices. Yeah, maybe I have time for that. So one interesting thing about the algorithm is, okay, when we construct this partition, we have to solve the problem of finding the closest integer point to a given vertex on a given facet. So this is understandable if I go back to my example here. So I have to find this sort of point here. So this is trivial, of course, in 2D, that's middle school math, but on a more, in higher dimension, this is less trivial. So how do I find a point which is close to a given vertex and a point which is on a given facet, okay? So the way we do that is by actually computing the integer hole of that facet. Because once we have its integer hole, so in particular we have vertices that are hopefully close to the point that we are trying to reach. So I'm going back here. And so that means that we have to solve the following problem. So computing the integer hole of a face, so of something which is in lower dimensions with respect to the dimension of the ambient space. And the way it's done is by using Hermite-Lamberts form. So to obtain a parametrization of that object in lower dimension, of which we want to obtain its integer hole. And once we have the integer hole of that object in lower dimension, then we can deduce easily points that are close to it, close to a given vertex on that object. And so that gave us the opportunity to create some interesting pictures. So for instance, here, so we have this facet here. So you can, sorry, you have this yellow region, okay? So you can feel this is the integer hole of one of the facets of that object, and this thing is computed in one dimension less. So as you can see here, it's almost flat. It is 2D, but it's so thin that I have the impression it is almost flat. And then we can see that indeed the vertices of that yellow region are close to the vertices of the original pyramid. And so this is how we can find points that are close enough to a given vertex of the pyramid. And then create that famous partition. Okay, I won't say much more about the algorithm. I will just, yes, here are some examples in Maple. So as the integer hole command of the polyhedral sets package. Okay. So we did two implementations, one in Maple and also one in C as part of the BPass library. And we compared our implementation against Normalise, which is a well-known library for this sort of computation, so dealing with lattice points and so on. So again, unfortunately, you have this null everywhere, but not in the paper. And so what we can observe, so we have different family of benchmarks, of course, in 2D and then later on in 3D and in higher dimension. So that this algorithm essentially, I mean, its cost depends on the geometry of the object and not so much on its size. So here we have objects that are all of the same shape. As we go to the right, the size of this object increases. But for us, the running time does not increase much, whereas let's say for normalies, it increases a lot, or even to the point where normalies cannot conclude. Okay, so what I've said are essentially in this conclusion. So the idea was really to design an algorithm that takes into account, I would say, the geometry of the input polyhedron. In particular, if the integer whole of that polyhedron is relatively close to the polyhedron, that is, you already have many integer vertices, then the algorithm should be cheap. And again, the algorithm should not depend much on the size or the volume, but it should really depend on the geometrical properties, like the number of vertices of the integer whole. But we have not been able yet to give some complexity estimates. That's something a little bit difficult. I don't know, so if anyone has any ideas, I would be very happy to have your suggestions. Okay, any questions about integer wholes? Okay. Maybe I will show a little bit of Z polyhedra. So, as we were discussing integer wholes, we mentioned Z polyhedra. So just to remember them, since we are going to use them again when we do quantifier elimination. So inside the polyhedral sets package in Maple, we have a sub-package called Z polyhedral set, so it's specialized in manipulating Z polyhedra. So for instance, here we build a lattice. Here we have a system of linear inequalities, and then we put these things together to build a Z polyhedral set. So as you can see here. So we see the defining inequalities, the variables. You can have parameters as well, and the lattice. When you create the object, you don't know if it's empty or not, so you can create a Z polyhedral set with anything. And the way you normalize it is by calling the integer point decomposition method. So now in the output, you have Z polyhedral sets which are normalized, so they have all these nice properties, they are consistent, and you can enumerate the points if you want by back substitution. So here in the decomposition, there is one main component of maximum dimension and 2 points. Okay. Also, this decomposition can be done in 2 ways. So either we use lattices, or for those of you who know about the omega test of William Pugh, there is also an output format similar to the one of the omega test. So instead of using lattices, you introduce new variables. Okay, so I'm done with integer wholes. Oops, moving in the wrong direction. And now we'll talk a little bit about the problem of counting integer points, of course, counting without computing them. Okay, so typical problems look like this. So say we have this for loop nest, and we ask the question, so how many memory locations are reached during the computation? Okay. So this can be, setting the problem into inequalities is relatively simple. Now, I will not insist on that part. So one can easily check that the set of the memory locations that are accessed correspond to the sets of the xy point, satisfying the system of inequalities. And so the question now is to give the number of the integer points there as a function of n. Okay, so of course we will see the answer in a moment. So first we have some examples with n equal 5, n equal 10. Okay, it is the answer, n squared minus 4, okay. So more generally, that's what we want to do, is to compute the number of the integer points of a parametric polyhedron. The parameters will always be on the right-hand side, let's say in the B vector. So we mean that each coordinate of that B vector can be a linear polynomial. But there are no parameters in the matrix A, of course. Okay. So why is that problem a little bit difficult? Because the shape of such a parametric polyhedron changes or may change with the parameters. So this was not obvious with the previous example, but this new example should make it clear. So here for these three different values of n, our parameter, so we see that we have 3, 4, maybe 5 vertices. So the shape of, let's say, the integer whole is changing. Fortunately, it's changing, but it is periodic. So this is what we learned from the theory of Eugène Erhardt. And so that means that C of B, the number of integer points as a function of our parameter B, is computable as a piecewise function, and this is what we will see in a moment. Okay, a little bit of related work. So maybe you have heard about peak theorem. So in the plane, if I have a little polytope, I can relate the number of its integer points on the border. So here we have to assume that actually the vertices are themselves integer points. I can relate that number with the number of integer points inside and the area. And so we have that formula. Unfortunately, there is no generalization of Peake's theorem in higher dimension. And this can be proved, actually, that it cannot be generalized. But, okay, we have Erhardt's theory, which gives us hope. Erhardt's theory, which he obtained by studying the dilatation of these parametric polyhedral sets. And we will see Erhardt polynomials later. Okay, but before we get to counting integer points of parametric polyhedral set, let us first count the number of integer points of non-parametric, because that's already not obvious. And this is done through the notion of generating function of a polyhedral set. So given a polyhedral set P, we are going to map every integer point E to a monomial, also in a natural way. When d equal 2, instead of writing x1, x2, of course, we will write x and y in the following examples. And then the generating function of P is the sum of the x to the E, where E ranges through the integer points of our polyhedron. So when P is a polytope, then this thing is a polynomial, otherwise this is a Laurent series. Okay, so let's do some examples. Let us start with the ray or half line corresponding to y equals 0 and x is non-negative. So these are some simple math. Okay, so I think everyone would agree with that. So we retrieve some well-known formula. Remember, this is a half line, so this is not finite. And now let's use this to compute the number of integer points of a polytope. Okay, so here is my polytope with these 12 red points. How is this going to work? We'll use a formula due to Michel Brion, which is telling us that the generating function of this polytope is the sum of the generating functions of its vertex cones. So here we have 4 vertex cones, four corners we can say. So we are going to compute the generating functions of each of these cones. Okay, so Q1 is the southwest cone. So that is the first quadrant. Okay, so again, this is some well-known thing. Okay, it feels like we go back to high school. Okay, so we get this series. Now let's move to the northwest corner, so Q2. Again, by using elementary transformation, we will manage to reduce to formula that we know well, and we'll manage to find the sum of that series. Okay? Let's continue. Now the northeast corner, Q3, okay, similar, doing some easy transformation. And finally, Q4, okay, southeast, so we are in the mini, up. We compute our series, and then we apply the theorem of Michel Brion. We sum these 4 series, and that gives us the generating function of our polytope. And we expect to see a polynomial, of course, because it's bounded. And now we can deduce the number of the integer points by specializing x and y to 1. And we find 12 as we expected. Okay. So as we have said, we took advantage of that formula of Michel Brion. But our calculations were relying, without saying it, on 2 facts. First, every cone here was simplicial because we are in 2D. In higher dimension, this is not going to be true. So we need to do something about that. And also, we could make this simple transformation on those series because these cones were given by unimodular rays. So we could make unimodular transformation. And so that's why computations were so simple. But in general, that's not going to be true either. And this is where now comes the algorithm of Alexander Barvinok. I'm sure you've heard about that. So first we have to reduce to the case of simplicial cones. So there are many well-known algorithms for doing that. And then from a simplicial cone, we need to move to a unimodular cone, that is a cone with extreme rays defining a unimodular matrix, so that we can do these easy calculations with power series. And that's the main point in the algorithm of Barvinock. And he could prove that this algorithm could run in polynomial time in fixed dimension. Okay. So how do we do that now with parametric polyhedron? So here I will do hand waving because things get a little bit technical. So what are the, but I will show lots of examples. What are the challenges? So first we need to find the vertices of the input polyhedron. Why do we want the vertices? Because we want the vertex cones in order to apply the theorem of Michel-Brion. But the vertices, they may change with the parameters, okay? But, okay, this can be done. We can say, essentially, we solve a bunch of linear systems, we do some case discussion, and we manage to find, I would say, the different configurations for the vertices. Once we have the vertices, we need to find the vertex cones. That is, for each vertex, we need to understand what's the cone attached to it. Again, that implies some calculation. Essentially, again, it's solving system of linear equations. After that, we can run the algorithm of Barvinock and manipulate a generating function. But then comes the trouble. So, in this calculation with power series, we managed to go back to situations for which we know to compute the sum of the series by doing unimodular transformations on the exponent vectors. The exponent vectors in the parametric case, they will be given by the vertices of the polyhedron. But these are objects involving now the parameters. In fact, one can see that the vertices in the parametric case will look like fractions. In the numerator, there will be linear polynomials, and in the denominator, you have numbers. So that is, you have maybe maybe n plus m divided by 3 expression of that form. Okay, and then these expressions will become exponents in those series. Okay, which is a little bit not so comfortable. So again, that implies some sort of case discussion that is deciding whether n plus m can be divided by 3, or is it congruent to 1 modulo 3 or congruent to 2 modulo 3. That introduces what is called quasi-polynomials, or polynomials that are periodic with integer periods. And that's what I'm going to show you now in the demo. Maybe you saw that, when was that? Tuesday? With Jürgen's demo. Okay. Okay. I think I should sit a bit more comfortable. Okay, so maybe Jürgen also has shown that, right? So a new feature in Maple would be polyhedral sets. Of course, we introduced that because of phase lattice. I'll skip that here. Okay. So yeah, so we can compute generating functions, of course, of non-parametric polyhedral sets. So maybe you're going to show these examples. And now moving to the parametric case. Okay, I will start with toy examples. So here is my parametric, a parametric triangle here, depending on one parameter n. And so my problem is to count the number of integer points. And so we get this formula that you see here, the formula 3.2, etc. Okay, which is what we expect. Okay? So far, so good. Okay, I'm sorry. The next example is a little bit more complicated. Still depends on one parameter. So sorry, I think I'm not pushing in the proper place. Okay. Okay, and now comes our first quasi-polynomial. So what is that? So you see in the square brackets here, you have two polynomials, okay, separated by a comma. After that, you have n and 2. So that means when n is even, you choose the first polynomial, and when it's odd, you choose the other one. And so that gives you your number of integer points. Here I have another example, so another family of parametric polyhedra. Here we have two quasi-polynomials. They don't always appear. Sometimes things look a little bit complicated, but in fact they may not appear. But if the geometry of the parametric polyhedron changes with the parameters, it's likely that they will appear. Okay, so that's going to be the case here, because the geometry is changing. Did I push? Okay. Yeah, so here we have three cases, so three formulas with quasi-polynomials. Okay, this one is simple. The geometry does not change, so no quasi-polynomials. We got three parameters, two variables, so then did I push? Okay, yes. And the last example, now in 3D, where again the geometry is changing with the parameters. But luckily, we did not get quasi-polynomials. All right. Okay. Any questions about that part? Okay. So, okay, the last part, sorry? We have what?
A bound on the periods of this quasi-polynomial. You obtain the parameter space.
If we have a bound on the...
Okay, so how long it takes you to go back to the same polynomial? Now it's a quasi-polynomial, it means that you have different polynomials according to some modular.
Ah, okay. Yes, so...
The bound exists, but did you try to do interpolation using the other algorithm in your case without parameters?
Yes, well, we use the other algorithm to verify, well, that's how we verify I would say, at the software level. But the two implementations are in fact one, because in particular, the decomposition into simple circles, obviously. So when we deal with rays, the parameters do not appear. Okay? The parameters, they appear when you deal with the vertices. And because the vertices are involved in the exponents of those generating functions. So this is where the two implementation diverge, essentially. Yeah. Thank you for the question. But essentially, this is a single body of code with that special case. Yeah. Thank you. Okay, so I'm skipping the slides. Explaining how we do the case discussion. The case discussion is a bit complicated because it appears several times. So typically when you do case discussion, let's say in triangular decomposition or this type of algorithm, you build a tree. Here, because you have to find those parametric vertices, you have to solve independent parametric problems. That is, you have to compute the different parametric vertices, and each such computation is a parametric problem. So you end up with a forest that you have to then merge into a tree. So that's why the parametric aspect is a little bit unusual. Okay, so last part, that's to some sense the final goal of all this, is to be able to do Presburger arithmetic. So what is Presburger arithmetic? This is first order theory of the integers with addition, equality, order, and divisibility predicates, that is predicates of the form, given integer k, I can say if k divides x. So there is no multiplication here, and this is why the theory is decidable. Okay? These things could be presented more formally, and I will just refer to the Wikipedia page of Presburger arithmetic. Yes? Well, first, because that allows us to solve more problems. And also, it appears naturally.
No, but I mean, you code it as there exists y such that y plus y plus y is equal to x?
Yes, I think you could, but that would really make things messy. Okay, I prefer to explain that over coffee because, okay, that goes back to some, yeah, I would say almost philosophical things. So yes, but I think it would be a bad idea. And to some sense, what I'm going to show will justify that. That is, it is very natural to describe Presburger arithmetic using Z polyhedral. So what is the Presburger formula? For us, it will be something in pre-next normal form. So that is, you first have a sequence of quantified variables followed by quantifier-free formula. So here, this phi of x1, xm, y1, yn is our quantifier-free formula. Of course, we are going to say what we expect to see there. y1, yn will be, in all the subsequent slides, our unbounded variables or free variables. So we can assume that our quantifier-free part is in disjunctive normal form. So it's essentially or of and of atomic formulas. And for the atomic formulas, okay, we have inequalities and divisibility predicates. Okay. And for me, I will assume that these inequalities are non-strict, even though I will talk briefly about Cooper's algorithm, in which case they are strict. Yeah. And so in these atoms or atomic formulas, so we have non-strict inequalities or divisibility relation of that form. So either we have L less or equal than 0, or K, where K is a literal, I mean a number. K divides a linear polynomial. By linear, I mean a polynomial of degree 1. It could have constant terms, of course. So calling Using linear is a bit of an abuse, but it's a convenient abuse. Okay, so Presburger arithmetic admits quantifier elimination. So that means for each of such quantified formula, we can decide whether it is true or false. And if it has those parameters, we can find conditions, necessary and sufficient conditions on those parameters for the formula to be true. This was first proof in the thesis of Presburger. There is a reference there, so it's possible to access it. A first modern proof was given by David Cooper. Again, there is a reference there. I would recommend also the famous survival guide to Presburger arithmetic by Christoph Haas. But we are also going to give here our own proof. That is why this is true. Okay, and we really focus, in fact, on the parametric case, that is in the formula. Again, we have two groups of variables, those which are quantified or bound. These are the x variables. And then there are the free variables, y1 through yn. So we are trying to find a subset D of y1, yn of zn, giving necessary and sufficient conditions for the formula to be true. So here is again my Presburger formula. If I have no bound variables, so if m equals 0, it suffices to compute all the points that make phi true, which can be done, for instance, by computing an integer whole. So I'm getting back to this in a moment. If m is positive, that is, if I have at least one variable to eliminate, I'm going to assume that f is of the form q, where q is either that exists or for all, x1, and then f prime, where f prime is free of quantifiers, because I'm going to build an inductive process. So by induction, I will assume that I have only one variable to eliminate. If the quantifier is existential, so what we have to do is what we call integer projection, and this is what we are going to describe in great details. If the quantifier is for all, then I can reduce to the existential case by Morgan's law, or doing double negation. But in practice, as much as possible, I should avoid that, because this is how computations will explode. So as much as possible, we should apply tricks or rules, something like this. If I have something of the form for all x1, for all dada, all xn, c times that vector equal q, then c and q must be 0. Okay, yes, I should mention Cooper's algorithm. We also implemented that, and our implementation is publicly available. This is a historical algorithm, so the first modern algorithm for Presburger arithmetic. So in this case, Cooper considered the following atoms. So you have strict inequalities. So you have two kinds, depending if you are giving an upper bound or a lower bound of the variable that you want to eliminate. The third atom is a divisibility condition, and the last one is the negation of a divisibility condition. Okay. But we prefer to think differently. So we rearrange our quantifier-free formula as a disjunction of what we call Z polyhedron predicate. So Z polyhedron predicate is a conjunction of congruencies or divisibility relation and non-strict inequalities. Okay, so this is what we have to deal with. Okay, maybe I should go back just to keep in mind. So in that Z part, again, we have linear inequalities, large inequalities, and then we have congruencies or divisibility relations. So first, we want to deal with the divisibility relations. Of course, we are going to use Hermite normal form. So let's say we have two positive integers, r and n. We have an integer matrix n with r rows and n columns. We have a vector z of indeterminates, z1 through zn. We have a vector q of dimension r. This is a vector of polynomials, linear polynomials as usual, in variables w1 through w nu. We're almost there. And these variables are seen as parameters, so this will become clear in a moment. And last, we have a vector m of positive integers. And what we are dealing with is something of the following form. So it's a system of congruencies. Again, we have the matrix n, the vector z, congruent to q, which is our vector of linear polynomials, modulo n, so meaning by this that each row is congruent to one of the coefficients in the vector m. So a sort of, I would say, parametric multivariate CRT. So how do we deal with that? So first, one can pretend that Q does not have parameters. And then by building the appropriate matrix and computing its Hermite normal form, we can find conditions for that thing to have integer solutions. And if in fact we take into account that Q has polynomials, that brings another system of congruencies that is solved by a second Hermite normal form. So at the end of the day, in applying twice Hermite normal form, one can give conditions for such a system of equations to have solutions and also describing the solutions. So with that in mind, now we will be able to process and put aside the congruencies that appear in our Z polyhedron. So remember, this is where we were. So we assume we have one variable to eliminate, and we have a bunch of parameters, y1 through yn. The quantifier free formula is a disjunction of things that are made of inequalities. This is coming here. Inequalities and congruencies. Okay, so now this is what we have to deal with. So find the values of y such that there exists an x, so that we have all these conditions satisfied. Okay, so the first step, as you can guess, now is to use the previous slide that for solving the system of congruencies. So what happens when we solve the system of congruencies? This will solve some of the variables. Possibly it will solve x, but let's say it does not. So after that, so we may still have some inequalities. And then we have, for the congruencies part, we have a lattice, okay? That lattice we put aside, consider that that part is solved. And now what we have to deal with is the system of inequalities in which we have replaced the solutions given by the lattice. Let's say if we have something telling us that y1 is given by something from the lattice, y2 is given by something from the lattice, then we substitute here, we still have to deal with a system of linear inequalities. Okay, so now what we have to deal with is system of linear inequalities over the integers. Yesterday was over the rationals, now the difficulty is over the integers. So what I've just explained with hand waving is stated here. So that is, I use my lattice. If in the middle of that I also detect some implicit equations, because this can happen, I use them. So I simplify as much as possible the system of inequalities. And now I'm going to concentrate on that part. So here I'm just repeating what I've said 1 minute ago. Okay, so now again I've put the congruencies aside because I've solved them with the lattice. And I need to focus on the inequalities. I will first assume that I have only 2 inequalities, and then I will go back to the general case. And I will assume that these 2 inequalities are a pair of lower bound, upper bound for the variable that I want to eliminate. So I use some notations, that will be convenient in a moment. So I have 2 inequalities, so capital A less or equal than 0, capital B less or equal than 0, and I write A of the form AY minus A times X. So little a, like little b over there, is a scalar, so I mean not just an integer, actually a positive integer, whereas AY and BY are linear polynomials. So that means this is all the terms of my polynomials except the term where I have X, the variable that I want to eliminate. And again, I can assume that here my little a, little b are positive. Please note that the sign. So one equation is what we call a lower bound for little x, and another one gives an upper bound for little x. Okay, so now our QE problem has become that exists x such that AY is less or equal than little x times x, and b times x less or equal than by, where again AY and by are linear polynomials. Okay, so we are going to solve that in 2 steps. There will be a first sort of direct way of doing that, proposed by Harris Williams. And then we will use the optimization due to William Pugh, and which is known as the omega test, that some of you may have heard about. Okay. So again, we have these 2 inequalities. Little a and little b are the coefficients of little x, the variable we want to eliminate. Little l is the LCM of little a and little b. And it's convenient to denote b prime as L divided by A and A prime as L divided by B. In a moment, we will be using that quantity, actually that set EK, which is the set of the y values, such that the remainder of the polynomial by with respect to the integer little b is k. So that gives a congruence, in fact, okay? So we will see that the following 2 formulas are equivalent. The first one is the one that we are after. This is our input. It is that exists x such that, okay, we have the conjunction of our 2 inequalities. The second formula is a disjunction for k ranging from 0 to b minus 1. And here we have the disjunction of two things. The first one says that y is in ek. In other words, we have a congruence relation. And the second condition is an inequality, where x now has disappeared. Okay, so why this is true? So first, if we were, let's say, over Q, so in the continuum of the real numbers, then we would simply do as usual, as in Fourier-Moskine elimination. But here we are over the integers, so we need to be a little bit more careful. Unless A equal 1 or B equal 1, in which case, okay, things are as simple as they are over the rationals. So I'm just going to assume that A and B are greater than 1. So I go back to my f of y over there to understand what that really means. I use my LCM. And so now what I have is that f of y is equivalent to del exist x such that L times x is between b prime times ay and a prime times by. So what we are saying here is that in that interval, b prime times ay and a prime times by, they are multiples of L. Okay, that's the meaning of that sentence, right? Okay, which is what I'm saying here. F of y says that a multiple of L lies in between these two things. Okay, well, there is one obvious multiple of y, which is given here. Sorry, an obvious multiple of L. So I take this polynomial minus the remainder of that polynomial with respect to L. Okay, that's an obvious multiple of L. And so, in fact, I have this equivalence here. So if there exists x, then that implies that. And if this is true, then there exists x as well. So these two things are equivalent. And I can do a little bit of manipulation here to take a prime out. And that finally gives me what I want. Why? Because now I want to say for each value of that thing, I have a condition. So that quantity, this is an integer, can be a number between 0 and b minus 1. So for each of these values, I have the condition shown at point number 2 in the statement of the theorem. Okay, this is relatively simple, but one can feel that this may introduce lots of, I would say, cuts, right? For each value of k, you will essentially produce a case in many disjunctions, so that's not ideal. So fortunately, there is a trick, a very important trick, to significantly reduce the number of these cases. And that's what is called the omega test due to William Pugh. So this is a sufficient condition for our interval to have integers. So again, the same interval that we are looking at here, this b prime ay and ay b prime. So if the following holds, then actually f of y holds. Okay. And that is done with, I would say, elementary manipulation. So maybe here I will skip the proof, because this is really high school math. So this is telling us that, yes, when that condition holds, f of y is true. But this is only sufficient condition. So we need to use the two theorems, I mean the lemma of William Pugh and the theorem of Williams, to get what is useful in practice. So f of y is true if either, okay, we have that condition that was given by the previous lemma, or we have all these cats. So to give an idea of how many cats we can have on a small example, let's say if A is 7 and B is 11, if we don't use the optimization of William-Pugh, then we have a k ranging from 0 to 10. Otherwise, k only ranges from 8 to 10. Okay, last step. So now we have seen how to do the projection for two inequalities. Then from there we can deduce the projection for many in some very natural way. So first of all, of course, if all the inequalities are lower bound, all the inequalities are upper bound, then no problem. The f of y is trivially true. Otherwise, we have to consider all the pairs of a lower bound and an upper bound. For each pair, we get the condition given by the previous result. Then we take the conjunction of all these things, because we do that for each pair. And at the end, after putting everything into disjunctive normal form, there will be two parts. There will be the part that I denote by S0, where you have only the inequalities coming from the optimization of William-Pugh, and that part is referred in the literature as the dark shadow. And then the rest, where you have a mixture of congruencies and inequalities, which is referred as the gray shadow in the terminology of William-Pugh. So I will not explain why here. And so that gives us a complete algorithm for doing QE, but also for doing projection, and therefore to describe the integer points of polyhedral set. So we did the two things at once. And now I can go back to demos. I will show the pre-executed version to make things fitting in time. First, I have some trivial examples, but they are good to show the input format. So that's the same for other package in Maple for doing quantifier elimination. So the same type of notation. So SQ is the sequence of quantifiers. F is the quantifier-free formula. For the moment, the command has a simple name, but later on it should have a better name. Okay, so these are just some simple examples to understand how things look like. Maybe here a little example with parameters. So to show, okay, we say something like there exists a y such that x is non-negative, x is less or equal than y is less or equal than z, and we want to eliminate y. Okay, so we get this in the output. Here we have there exists a y and a bunch of inequalities. So essentially, yes, projecting system of inequalities, but projecting in the sense of the integers. Here this is still relatively simple because we have only two variables, x and y, so we have these conditions about x. Okay, things get a little bit less trivial because we have there exists I, j, k, and a free variable n, I think. Maybe there are other variables. Oh yes, there is x and y. Okay, here this is an interesting case where the solution is just of the form xy belongs to this lattice. No inequalities here. Here we have a mixture of lattices and inequalities. This is still, yes, for existential. And finally, here, yes, we have an elimination of universal quantifiers. Okay, in this case, the formula is false. So we did different implementation. One again, which is based on these Z polyhedral sets. There is another one which is based on the on counting integer points, so based on Barvinock's algorithm. And the last one based on the historical example, algorithm of Cooper, but this algorithm is much less powerful. It can only solve essentially a system in 2 variables. Experimentally, the one based on Z polyhedral sets is the one doing the best. Okay, I think I should stop here. Thank you.
Okay, questions for Marc? You don't need microphone.
I can speak, don't worry. Thank you very much for the nice talk. I have one question. In general, I want to add polygons. Do you provide any kind of functionality for this? Do you have any specialized algorithm or something that you can use now in the implementation?
Specific to polytops?
I have 2 integer polytops and I want to compute the Minkowski sum of this.
No, but I would be happy to hear more precisely which problems you have. But essentially, I've shown to you essentially, yes, all what we have done. Again, my main interest is those parametric things and quantifier elimination, but I hope that this library can keep growing, so I'm happy to hear about any suggestion. And I have many students who will be happy certainly to work on this.
Okay, any other question? Okay, if not, let's thank the speaker.
Thank you.